right, let's begin. Last time we started talking about series. So remember, this is just the sum of the terms of a sequence. So the notation is sigma an, and this just means a1 plus a2 plus a3 plus dot. Of course, you can have a finite series, but we don't care. They're not very interesting. We care about adding up an infinite number of things. Okay, and we say the series an converges to S if the limit, if Sn approaches S where Sn equals the sequence of partial sums of the series. So, i.e., that's saying we can say this series n goes from 1 to infinity of an can be equal to the limit of Sn equals S, where Sn is just the sum of the first n terms. And if S is a real number, this guy converges to S. And we take that number S to be the sum of the series. And last time we actually also looked at a telescoping series in which our sequence of partial sums, it had a special form that almost all the guys actually canceled out. So we looked at telescoping series. So these guys are where most terms in Sn cancel out. So that we can find the limit of Sn easier. Now, not all series have this property, but the ones that do, we call them telescoping series, and we did an example of that one last time. So that guy was a telescoping series, because I believe we showed that this was equal to n minus 1 over n plus 1. And we showed that that actually converges to 1. Just to jog your memory of where we left off last time. Now, we're going to continue with this kind of idea, figuring out when does a series add up to something meaningful. It's a very important thing. Another thing you want to remember, and again, this is just a repeat of last time. We say this guy converges absolutely if the series with absolute values around the terms converges. And converges absolutely, very important thing because of the rearrangement theorem. Things that converge but don't converge absolutely. An converges conditionally if An converges, but if I throw absolute values around the terms, it does not. Conditionally convergent sums, they're kind of fickle. I can change the value that they add up to by rearranging the terms, which is bad for a lot of math that we'll want to be able to do. So absolute convergence is going to be important to us, and as time goes on, we're going to start working our way into absolute convergence slowly. But before that, we just want to be able to talk about convergence in general. Knowing if and to what a series converges. is important. Muy importante. So that's what we're going to explore. Now, the if question is easier to answer than the to what question. Most of the time, this is going to be out of reach for us in Calculus 2. That's going to be above our pay grade. Most of the time, we're going to focus on if something converges, not necessarily what it converges to. There are going to be two exceptions to this. One of them is the telescoping series. If a telescoping series converges, you can find the exact answer. I showed you how to do it last time. The other scenario where we can actually tell what it converges to without doing anything too crazy is something called the geometric series. I'll talk about that today. But pretty much in any other case, we're not really going to know how to find out what the answer S actually is. We're just going to want to find out, does an S actually exist? Is the answer out there somewhere? And so, sections 10.3 through 10.6 deal with the if AN converges. And after that, we're going to get into something called power series, and that's going to be pretty cool. But now I'm just going to go through these sections. I'm not going to label the sections when I'm going through them. I'm just going to tell you what they say, just keep the flow going straight. But what we're covering from now on is like from 10.3 onwards. So that's what we're going to do. And I'm going to tell you a bunch of ways that we can determine whether or not a series actually converges to something meaningful. We are then going to try to apply this. Not any crazy applicable way, but in your future classes you'll be applying that. Right now we're just going to study the series as a general topic. Okay, so moving on. The next thing I want to talk about. So what we're going to do here is a series convergence test. Which, tell you about all of them. They're going to be about 9 or 10 of them. I think should take 2 classes, might spill into a third, but that's what's important. So this is a test that tell us whether AN converges. And test 0 is the telescoping sum. So let's move on to the others. Test number 1. So here's something called the test for divergence. Now there is a test that's going to be easy for us to tell if something diverges. It's called the test for divergence, aka might be called the nth term test, might be called the kth term test. Some people call it the limit test, but I think thinking of it as a test for divergence, thinking of it under this name, is much nicer because it tells you about divergence. It actually won't tell you that something converges, it'll actually tell you when the convergence is not going to happen. And so it comes to us in a theorem that I'm not going to prove, but it should make sense once you actually think about it. So, like A and B, an infinite sequence series. Here's what it says. If the limit of AN is not 0, then AN diverges. And that's it. Now, this guy here is one of the easiest tests to apply. So it's going to be one of the things that you're going to, if I give you a random series and you have no idea where to start, chances are you'll probably start here, or at least glance at it to see if the limit is going to be 0 or not. Because if it's not 0, then there's nothing else to do. If a series converges, its limit must be 0. So at this point, it's very important that I show a warning here. Again, reading mathematical statements, it's very important that you read them exactly. Notice that I did not put an if and only if. I did not do like a double arrow or something like that. I made the statement in one direction. If the limit is not 0, then the series diverges. You cannot assume the opposite is true. Just because the limit is 0 does not mean it converges. So if limit of AN equals 0, it does not mean AN converges. So that's important. So if you look at a series, you take its limit and you get 0 as the answer. Don't assume it converges. You cannot do that. You have to try something else, try some other test. But if you find that the limit is not 0, you can definitely for sure conclude that it's going to diverge. This is called the test for divergence. That's why that's important. It can only tell you about divergence. The limit, whether or not it's 0, only tells you about divergence. It does not tell you about convergence. Okay? So don't do that. Don't be this guy. Always have a lot of students just take a limit, show me it's 0, and they say, oh, it converges because the limit is 0. Not true. There's a famous counterexample to this. Does anyone know what the famous counterexample is? Pretty much every math textbook that mentions this, they always use a certain series as the example to show that this is not going to be true. And the famous counterexample is something called a harmonic series. Now the harmonic series is a very specific series. This is the series n goes from 1 to infinity of 1 over n. So that series specifically is called the harmonic series. Very useful in signal and auditory processing. So if you go down that road, it's going to be a very important series to you, but it's called the harmonic series. It is a famous series that diverges. It is known to diverge. Right? So if you add up 1 plus a half, plus a third, plus a fourth, plus a fifth, plus a sixth, it actually doesn't add up to anything. It actually goes off to infinity. So that's a very famous divergent series, 1 over n. It's called a harmonic series. You will notice though, but of course if you take the limit of 1 over n, you get 0. But this guy diverges. Another famous example that tells you that a limit of 0 doesn't really tell you much is series 1 over n squared, and goes from 1 to infinity, is known to converge. In fact, has anyone seen this guy before, knows what it converges to? So this is like 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. Yeah?
Is it P series?
It is a P series, but what is the answer?
Good question. Is it divergence? Because v is equal to 2? No.
It's known to converge.
Oh, 0.
Right?
What is it?
So that means 1 plus a fourth plus a ninth plus a 16th plus 1 over 36. We're just adding these guys up. That actually adds up to something. You'll never guess what it adds up to because it's crazy when I'm gonna tell you what it adds up to. Pi squared over 6.
What?
Makes no sense, right? Pi is not even a rational number. How is it that I added a bunch of fractions and got a pi squared? But that's actually what it adds up to. We're not going to see in this class how that will add up to. Not that it's hard to show that, but you kind of need something from Calc 3 to see that. That's one of the easiest ways. But this is known to diverge, 1 over n. You'll notice that the limit approaches 0. Here, also, limit approaches 0. So you can have limit approaching 0, but you can diverge or you can converge. So limit equals 0 means nothing. You can have either case happen. Limit not equals 0, though, it always means divergence. So those guys are important. And yes, these guys are both examples of P series. This is a test we're going to talk about, and we're going to use that idea to prove that this one would converge, whereas that one would diverge. But there are actually many proofs that show that this one would actually diverge. Yeah, so that's that. Test for divergence, that's it. Find the limit. If it's not 0, it diverges. If the limit is 0, it tells you nothing. Okay, so you just move on to something else. So that's the first one. So I'll mention that. Test for divergence. Yes.
So when you use the divergence test and we get 0, so can you assume that it's never going to diverge if we use any other series? I mean, if you use any other test? Like for example, we use the
if you try to check the limit and you realize it is 0, then you must use another test to make any conclusion about it.
But after using the divergent test and we find that there is equal to it's not, wait, never mind.
If you get it's not equal to 0,
Yeah.
it diverges. You don't do anything else. It
But
diverges.
if I get equal to 0, so can I be sure that it's never going to diverge? Or it's
No,
going to diverge?
you can't be sure at all. So the test for divergence only tells you about divergence. It will never imply anything else. But it is among the easiest tests to apply. So apply it first. Unless there's a good reason to assume that you know it's not going to work out, it should be one of the first things you think about. Just in the same way that if I give you a random integration, you kind of think of a basic rule first, or substitution would be one of the first things you think about. So too, when it comes to a series converging, the test for divergence should be one of the first things you think about. It's not going to always work, but it's really quick to check if it's going to diverge using the test for divergence. So just take a couple seconds, do the check. If you don't get 0, you're done. You don't have to do anything else. If you do get 0, you have to do something else, but at least you won't waste a lot of time. So it's one of the easiest things to apply, so just apply it. Test for divergence. If the limit is not 0, the series diverges. The test tells you nothing else. That's all it tells you about divergence. Okay. Let's go to test number 2. Which one do I want to tell you about next? Oh, maybe. Should I give some examples? Maybe I'll give some examples. I mean, it's kind of silly to give an example, but. Do the following converge. That's the first one. That's the second one. let's jump into it. A. So you see something like that? We introduced this concept last time called n factorial. So you see something like that. Now there are other cases in which you would actually try a different test that I'm going to tell you way down the road. With this, once you see a factorial and exponentials, there's a certain test that should come to mind immediately. It's called the ratio test, but that's way down the road. But from now, recall, you don't actually need that here, that this idea from last time. So because you know about this relationship, that's going to tell you that n to the n is much bigger than n factorial. So because you have that in mind, which you're not necessarily going to write down, you're going to know that since the limit is n to the n over n factorial equals infinity, the series diverges. That guy is not going to have an answer. It will diverge just by using right? Because infinity, in particular, is not zero. If you look at B, we need the absolute values here. So you see something like that. What is the limit as n approaches infinity of sine squared n? Huh? What's this limit? Huh?
Does it not exist?
It's not one.
Zero.
Yes.
The face he made, I was so confused.
Because I'm surprised that you guys are saying it so timidly. Like you should know that does not exist. Like, you should be like, doesn't exist, Jhevon. You should have like, it's like, no. In particular, that's not zero. Series diverges. If you look at, and that's it. See, like it's so quick to apply this test. You might as well do it first. Because there are some things you can just look at and be like, that limit is not going to be zero. C. What can you tell me about this one?
Zero. So that's one.
Three.
Well, the limit of 5 minus 7n plus 3n cubed over n cubed plus 2n squared plus 1 is 3. In particular, it's not zero. The series diverges. Right, so this is literally all the work you would need to show if this series showed up on a test and I asked you, does this converge? And you're like, you do write this line down, tell me it diverges. That's it. D. Look at this one. So the limit. What is the limit?
Wow.
Jeez. See? That's what happens. That's what happens. You do too much math, and that always happens. You get the answer when you don't mean to get it. Okay. That's zero. Anyway, what can we conclude now?
No.
Huh?
I mean, I'll try another. You got the choices.
Right. No conclusion. I was waiting for someone to tell me, oh, it converges, right? Let's throw this on. No conclusion. Can't say anything here. Not by this test alone, right? So you get a limit equals 0 means nada, right? You cannot make a conclusion based on that. Okay. If the limit is not 0, you can definitely conclude it diverges. You cannot conclude anything if the limit is 0. Okay. Let's go on to the second test. So what about a geometric series? Probably something that you've seen in high school. But it's also a very particular kind of series. This is a series of the form. So geometric series look like this. If you start them off at 0, it would look like A times R to the n, where A, R, non-zero are constants. Your A is the first term. Or another way to look at it, if you start a series from 1, which sometimes happens, then it must look like A, R to the n minus 1. That way when you plug in n equals 1, you still get R to the 0, and A gets to be your first term. So these two forms specifically are called geometric series. So example, 2 times 1/3 to the n is a geometric series. Or if you look at this guy, which this is the guy we actually saw last time. You could think of this as 1 times a half to the n. This is a geometric series. This was the thing from Zeno's paradox here. You start plugging this in, you get a half plus. We know that that adds up to 1. We'll come back to that. Or I think you get the idea. If you have 4 over pi to the n, you see something like that. This is a geometric series. So you can think of this as 4 times 1 over pi to the n. Technically for this one, you probably want to write it as a half minus n minus 1. Right? So you have to get it to fit into this form. The reason why is going to be clearer later. We actually know exactly when this guy converges. And let me show you. So you have a series, n goes from 0 to infinity of a r to the n. Now what does that guy actually look like? Well, you'll notice it starts out with a number like a, and it keeps actually multiplying by some other number. A fixed number r. So it starts out with a plus, then it multiplies a by r, plus, then it takes ar times r, plus, right? And it does that. So it starts off with a number and it keeps multiplying by r to get successive terms. Things like that are called geometric. Now, let's actually figure out when this guy converges. Here, notice that your Sn that's going to be the first n terms. I think that's the first n plus 1 terms, but whatever, doesn't matter. What you can do here is that little trick that baby Gauss used to add up the sum of the first n positive integers. one thing that you can do is you can multiply this equation by r. It's a finite sum, so you can do that, multiply both sides by r. Notice that you would get a times r, let's line it up here. You end up with that. And what you can do here, this is equation 1, call this equation 2. I am going to subtract. So if I take 1 minus 2, we get 1 minus r Sn equals, well, this guy kills that guy, this guy kills that guy, this guy would die here, this guy kills the guy before here. Everyone dies except these two, a plus ar to the n plus 1. And this means a formula for Sn would be that guy. So now, take the limit. Take the limit of Sn. That's just the same as taking the limit of a times 1 plus r to the n plus 1 over 1 minus r. Now tell me about that limit. What is its value? Now this part here is a constant. So the value is definitely going to depend on this part here. Now what is that part going to be? So if I take a number and I keep raising it to larger and larger powers, what happens? What are some numbers that we know?
It just gets bigger. Like, doesn't it go to like infinity then?
Does it? So these guys always diverge? There are times when it doesn't go to infinity. Can you give me an example where it won't go to infinity? If r is equal to 1, what would that give you? What's 1 to the infinity? Indeterminate, right? Which doesn't mean anything. Okay, so that's not gonna converge if r is equal to 1. Give me some other. It's a fraction, like 1 over 2. Okay, so if you take 1 over 2 and you raise that to larger and larger powers, what's going to happen?
It gets smaller.
It gets smaller. It approaches what? It actually approaches 0. What if I took, say, minus 1 over 2 and kept multiplying?
Doesn't it oscillate? It's undefined, isn't it?
Yeah?
Wouldn't it be an alternating series?
No, this is a sequence, so it's not a series. If I'm plotting the trend line of that sequence, where is it going to go? It also goes to 0, right? Take minus half times minus half, you get positive a quarter. Then you multiply that by minus half, you get minus an eighth, right? So yes, it's going to be alternating as you go on, but they're going to squeeze into 0 as well, right? Tell me something that's not going to work, that's going to not go to 0. Huh? 2. You have 2 to the n. What's going to happen to that as n goes to infinity? That goes to infinity. Okay, so some very suggestive examples here. So now tell me what do you think is going to happen to this guy?
It becomes 0 or infinity.
What are the cases? Tell me the cases.
R is greater than or equal to 1.
if R is less than 1.
Right, so if R is greater than or equal to 1 in absolute value, that's what I meant to indicate by this negative sign. Negatives and positives aren't going to matter. It just says if R is greater than 1 or equal to 1, then Sn diverges. And what if R is less than 1 in absolute values? Right, so anything strictly between -1 and 1, what's going to happen?
Wait,
Using 0.
it becomes 0, so we wouldn't, we still wouldn't know.
What becomes 0?
Like the limit.
No. What is Sn? Sn is this whole thing, right?
Yeah.
Now, look at this whole thing. My R is something that's smaller than 1. What's going to happen to that whole thing?
Or just approach maybe over 1
That's what's going to happen. If my R is someone smaller than 1, this part here is going to go to 0, and I'm going to be left with A times 1 over 1 minus R. So, that tells you when a geometric series converges, i.e., you can even think of this as a theorem if you want, that's kind of a proof. The series AR to the n goes from 0 to infinity, converges, in fact, if and only if R is less than 1 in absolute values, and it converges to A over 1 minus R. So this is called a geometric series. So this theorem here, this is called the geometric series test. So when you're looking at a geometric series, the geometric series test. That's the test. You have a series that has this form specifically, or of course it starts at 1, but you have an n minus 1. All you want to do is check, does that number that's being raised to the n, is that number less than 1 in absolute values? If it is, it converges. It will go here. And if it's not, then it will diverge. And in fact, this is something that, because I kind of showed that it doesn't matter if the R is positive or negative, it will automatically mean, in fact, the convergence here is absolute in the sense that if I throw absolute values around it, it's not going to make a difference. It's still going to converge. Here's a nice example. Remember that guy that we looked at last time? 1 over 2 to the n goes from 1 to infinity. Right? That was the guy a half plus a quarter plus an eighth plus da da da. Notice what you could look at this as. This is the same as a half times a half to the n minus 1. What you'll notice, this is geometric, with A equals a half and R equals a half. And since your R is less than 1 in absolute value, we know that this converges to A over 1 minus R, which is a half over 1 minus a half, which is a half over a half. And again, we know how to cover a mile. Right? So if you were to see this guy, remember last time we actually showed that this was 1 from by like writing out what the partial sums look like and figuring out a formula and then da da da. Yeah, this is a much quicker way to do the same problem by recognizing that that guy was a geometric series. Yeah.
Is it okay to have A as equal to 1?
No. You mean if just imagine there was a 1 here?
And then make that like half the n.
Right, so that would be incorrect because A has to be the first term.
Okay.
So in fact, if I pretended A was 1 here, I would actually get the answer 2, which is actually the wrong answer. Okay, let's look at some more examples. We can get like different volunteers to like so let's go through 3 examples. Now what you're going to notice is, I don't know if it's exactly like integration, but any individual test I tell you about is not going to be a big deal. Oh yeah, okay, I can see what's going on. Right? It gets tricky when I'll throw a bunch of different series at you and I'm not going to tell you who would behave with what test, and you have to kind of figure out which one to choose. We'll do that later, but that's the geometric series. Not much to actually say here. You see something that looks like this? Do that check. If that's true, it will converge to that. If that's not true, it diverges. 3 examples.
Wait, I think it's only E, because you root E over pi n plus plus. Over there is root E to the n.
Yeah, that's
Yeah, there's
But you didn't put the n.
what? Where?
You didn't put E to the n on the first question, but also.
Yeah, that was oh yeah.
Yeah.
Yeah, that one was intentional.
Yeah.
Okay, volunteers? You want to try the first one?
Yeah.
Okay, who wants to try the second one?
I'll take it.
Okay, all right. Who wants to try this one? Okay, Devin's gonna try this one. Oh, Sarah. She volunteered. She saved. I saw my look away. And when he looks down. Okay. All right. So we got the 3. Okay, everyone else. I'll give you guys like 3 minutes to actually come up with the answer here.
Okay.
And then we're going to go through them one by one. Everyone else, pick your favorite, go after it, and see if you get the answer at the end. 3-minute window here.
Good job. Never volunteer.
That's okay.
You gotta make sure it's in the right.
Everyone should be trying at least one.
It's the right.
Whichever one looks the scariest to you, do that one.
you took the equation out for me. Yeah, I took the first one.
Give you like 1 more minute.
Yeah, so that's why the rearrange the equation. Because I have to rewrite it. It's something like this. This one, so this is your A, this is your R, A and R. You just express it. You want to express it as one is as a one, so you want something like this one there. So all I did was pull out I squared. You multiply these together.
The A is A to the E to the pi. What do you express
The first one's that. E over pi over. All I did was literally try to get it in some form of A times R minus 1, right? Your R minus 1, it will be something here. This is your N minus 1. So I have this one. Now this is your A. So A over 1 minus pi. Or it will be something like this.
Alright, 15 seconds, wrap up.
This is what it should converge to. This is what it should converge to. Your A is this term. Otherwise, you don't have, otherwise, like right now you have pi squared and plus 1. You want to express it. I know, that's why I said you have to express, you have to rearrange it. So if you pull out like pi squared, right? Because if you multiply any two, if you multiply the power, you just add the right. If you add 2 here, it'll be n plus 1, which is the same thing. Oh, this is algebraic manipulation. I'm manipulating so that it's A and my R. That way, then you can say, because it's geometric series, A over 1 minus
Okay,
1.
time's up.
Right?
So who finished like 1 of them?
That was.
Is there anyone who finished 2 of them? You finished 2 of them?
Oh, it's right there. Yeah, okay.
Did you finish 3 of them? Anyone finish 3 of them? All 3?
That's too much to borrow.
Okay. So Devin, what did you think is the answer for this?
Yeah, converges to E over pi squared over 1 minus 1.
E over pi squared?
No, well, the E over pi squared is the numerator. I didn't simplify.
Okay.
E over pi squared is the numerator over 1 minus 1.
Okay. And you did this one?
No, I didn't.
You skipped this one. Okay. What do you think about this one?
That one I have to agree.
I think that diverges. All right. Anyone else who wasn't originally called upon have a guess? Did anyone do this one? Yeah? What do you think is the answer here?
1 over 4 over 1 minus E over 4.
Okay. So the actual official people who should have done this, do you agree with these answers?
I mean, for the first one, I knew is convert because E is less than the pi, but on that part, yeah, I got up to that part, but I didn't know how to simplify to that.
But you got this.
Yeah.
The rest of you did this, got this?
I agree that it converges, but not exactly what it converges to.
Oh, well, what did you think it is?
Well, I haven't got an answer yet, though.
Does anyone think this converges? So there was some disagreement on the answer to this. Did anyone else do this one? Has anyone got a different answer than this one for this one? Yeah?
I got E pi over pi minus 1.
E
Pi
pi
over pi minus 1.
over pi minus 1.
I did some simplification.
Okay. So it means that your original answer didn't have the square then. Because without the square, this is equal to that. Okay, great. Let's see. Let's see what do we have. Okay, all right. Tell me how to do this.
Okay,
What did you do? Tell me.
So it's the it's U over pi square plus that. Like I first wrote the first, second, third, and then so it's E over pi square
pi squared, okay?
Then the second term is gonna be e to the pi to the third. I mean, I'm writing like the first, second, so it's gonna be plus.
Oh, you're writing it out? Okay.
So I'm reading the first term, and the second term would be e to the pi to the third.
E over pi to the third?
Yeah,
Okay.
and then after I didn't write it, so I got the a is gonna be e to the pi over 2, and the r is gonna be e to the pi. So from that, since e is
Oh,
less.
so you notice that this was your A,
Yeah,
and then you figured out
that's my r.
to go from this step to that step, you had to multiply by what? 1 over pi? Is that what you realized?
I mean, I was just adding a value for n. So you know the original equation was n plus 1. So I just adding 1, 2 to the n to get the first term, second term.
Yeah.
And after that, I got was a. And for the r, I just went to the original equation, and then I could tell that because if you think that you can, I don't know how to.
So what is your R?
So my r is e to the e divided by pi.
So you think that's the R?
Yeah.
So now you think that this goes to A over 1 minus R, which means you had E over pi squared over 1 minus E over pi?
Yeah.
So you got something totally different. Does anyone agree with that? Like, is that okay? So that's not correct. So let's look at another way to do this. How did you? Who told me this?
I did.
Okay. What did you try to do?
I tried to write it in like the
Okay. Which is
so it would be the summation or any function we're gonna do. E over pi squared times 1 over pi to the n plus 1.
to the.
N plus. Or is it just n?
That would be n plus 1. Because if this were n plus 1, when you multiply across, you get n plus 3, right?
Yeah. So it would just be n.
Well, this is n, you multiply across, you get n plus 2.
Okay. Change the e over pi to e over. The e over pi squared to e over pi to first. Yeah. And then that's 1 over pi to n. Yeah.
Okay, so your A is e over pi, and so A over 1 minus r in this case would be e over pi divided by 1 minus 1 over pi, right?
Yeah.
So where did that square come from?
Yeah, I messed up on the
Also not correct.
yeah.
What happened? I prefer this method in general, but something is off. What's off? Yeah.
So I picked A to be E.
A is E.
Oh wait.
A can't be.
Or 1 over pi.
Isn't your
Right, so if you plug that in here, you would get that.
Yes.
Yeah, not correct.
Wait, for that one, isn't there supposed to be like a squared on the pi, on the A? Like, isn't that supposed to be e over pi squared?
So it's supposed to be a square?
Yeah.
And then you should have,
N minus 1 on the
Yeah.
for the ER.
Why?
Because the n equals 1 on the summation.
So pay attention, right? N equals 1. So remember what geometric meant. It means two things. If you start the series from 0, it looks like AR to the n. If the series starts from 1, it's AR to the n minus 1. This started at 1, which means you need to finagle it to look like this version, not that version. So you don't want a power n, you want a power n minus 1, right? So that's the first thing you're going to notice. If you're thinking this is geometric, which you're going to get used to actually trying identifying some of the geometric later on, but once you kind of guess, yeah, this might be geometric, how you put it in the right form is going to be important because it depends on how it starts off. You have to write it in such a way that your A is going to be the first term, right? Now both of these will look like this when you actually write them out. So I'm seeing this, and you realize it's geometric. You need to get it into one of these two forms. Seeing that it starts at 1 means this is the form you want to get it into. So that's going to be your first step. I think this is geometric. In order to know what it converges to, I need to get into one of these two. It starts at 1. That's my goal. I need to write it this to look like that. Okay, so once you know that, here's how you're going to continue. So first, you want to separate the parts that have the n powers from the ones that don't. So you would start out by you look at e over pi times 1 over pi to the n, right? That's how you would start off. Then I would notice that, oh, this starts at 1, so I want actually n minus 1. So I would actually factor off an extra pi, so I can do that. Then the next thing I would get is, well, now this is e over pi squared times 1 over pi to the n minus 1. And now that looks like this, right? This here is my A, and this here is my R. That looks exactly geometric now. And so this guy would approach A over 1 minus R. So that's actually the answer. If you wanted to simplify that, you'd multiply top and bottom by pi squared, I think. So that would give you E, this is equal to E over pi squared minus pi, which would probably be the nicer way to write it down, but this will be fine. Now, what I was going to do is if you got it correct, I would have given you like an extra bonus point on the quiz. You did get it correct, but you ended up changing your answer last minute, so no bonus point.
Yeah.
Let's see if we can get our friend who had this guess a bonus. All right, so what do we do here?
We want to get it in the form of A times R to the n minus 1.
Right.
So
How do you get it in that form?
I pulled out the. I first broke into fractions and then pull out the.
So what would it
the
look like?
column. So it'll be 1 over 4 to the n plus 1 plus e to the n of 4 to the n plus 1. And I basically pulled out a fourth.
Okay.
So it'll be 1/4 times 1 over 4 to the n plus e to the n over 4 to the n.
Then?
I kind of recombined the two, so you have 1 plus e to the n over 4n, and then treated that as my quote-unquote r. Not quite sure if that's correct.
Yeah, I'm not sure why couldn't you just factor out a 4 from here and then immediately go here?
Yeah, I was just doing steps, but
Okay. So now what?
And then I'd say like the fourth was the A, and then that whole thing there is like raised to the N. Not quite sure that's true.
A equals,
The 1/4. And then your R is supposedly 1 plus E over 4.
make sense? Everyone agree?
Wait. When you raise that to the N, I don't think that's the same. Like, cause, yeah.
What, you mean this is not the same as that? Well, I mean, to the end.
No.
Why not?
Because you're gonna be, like, once you start raising the power of N, you're gonna be multiplying 1 plus E times 1 plus E times 1 plus E. Like, yeah.
Yeah, so what did our friend do here? This was a blasphemy.
I did say quote unquote.
What you did was you distributed a power across a sum. That's what told your mind that this jumps to that. It does not. In fact, splitting it up was actually the correct move to do. You recombining actually shot yourself in the foot. So let's go back here.
Alright, well that's wrong.
You were getting warm here, but then you just went right back, right? So far so good. How would you fix your next step without doing any blasphemies? Huh? Distribute the summation. We have a property of summation that says the summation of a sum is the sum of the summations.
Oh my god.
Right?
I just missed that too.
Completely forgot.
It's actually, so now what happens?
We have 2.
That's like 1/4 to the N, and then that's E over 4 to the N.
So this is 1/4 to the n, and this is e over 4 to the n. Okay, and what can we do with that?
Check the convergence of both.
Yeah, it's 2 separate geometric series. It was 2 geometric series combined in one. Unfortunately, this was the wrong answer. The reason is it's the same. I think it's the same mistake. It was kind of a distributor of powers across some. Kind of ignored this part and took the quarter as the A and then took the R as the E over 4, which is not technically correct. So the trick here was to actually split it up. Because with that 1 here, it's not geometric with that 1 because you can't write it as A times R to the N. You have to split it up first, and you write each individual as A times R to the N, where in fact your A would be like 1. So it's 1 times a quarter to the N, and it's 1 times E over 4 to the N. So ultimately, the answer is what here? So it's a quarter times, what does the first series add up to? What's your A?
1.
It's 1. What's the R for the first step?
4.
1/4. Oh yeah.
Okay, so what does it add up to?
4/3, yeah.
You don't have to simplify, just tell me the basic.
Oh, like 1 over 1 minus
1 over 1 minus so forth.
Yeah.
Right. Plus this one.
1 over 1.
1 over 1 minus E over 4. So you can multiply the 1/4 in, that gives you 1 over 4 minus 1 plus 1 over 4 minus e. So this is going to be 1/3 plus 1 over 4 minus e is what this guy adds up to. It's two geometric series in one. To get it in the right form, you had to split it up. Otherwise, you're actually doing a distribution of sums, of powers across sums mistake. Because that 1, you can't just think of it as all of this to the n. It's just the e that's to the n. So you split that up, rewrite it in the right form. It starts at 0, so it means you want someone to the n, not to the n minus 1. So we just had a quarter to the n, so that means your a is actually just the 1 that's sitting beside it. So it's a over 1 minus r, going to be what that converges to. Because my 1/4 is less than 1 in absolute value. Also, e over 4 is less than 1 in absolute value. E is 2.71828. So yeah, that's actually the answer. So yeah, trick question. Well, not trick questions. It's a sum of two fractions. Just split it up. We just saw the property that summations distribute across sums. You can treat it as two separate geometric series. What about this one?
I think that one converts to 1 over 1 minus 3 over negative 3 over 2.
So how did you actually write that?
So the a is the first term, what is 1,
Yeah.
and r will be the terms that, actually the second one will be negative 3 over 2.
Right. Well, a couple ways you can see this. One, you can notice that I could actually write this as the series of minus 3 over 2 to the n. Another way you could realize that this is 1 times minus 3 over 2 to the 0 plus 1 times minus 3 over 2 to the 1 plus 1 times minus 3 over 2 squared plus 1 times minus 3 over 2 cubed, so on. Okay? So, you think this adds up to?
It starts to 1 over 1 minus negative 3 over 2.
So it's 1 over 1 plus 3 over 2.
Exactly.
Okay? Do you agree? No, that's wrong.
Divergence.
What happens?
It's more than 1, isn't it?
Diverges. Why?
Because this is the bar, the absolute value of bar is
R is minus 3 over 2, which means the absolute value of R is 3 over 2. It's bigger than 1.
Wait, didn't someone say that?
Diverges.
The first bracket.
So diverges. No, does not go to that.
We actually said salty.
This is good. We're seeing like mistakes happen in real time here. This is good. So you won't make the same mistakes on a test. Because yeah, so this actually diverges. So A is equal to 1, your R is equal to minus 3 over 2, and you would say since absolute value of R is greater than 1, the series diverges. Let's just so you went, Kedwin went, who else? Sarah gave some input. Who else? What's your last name?
BLA, but
Okay. And what's your name?
I don't know.
Last name?
M-A-M-A-K-O-R.
You too, right? Where do you go? What would be your question?
I guess I'll
Was it Gurov? What's your last name? This list is too long. You. Yes?
Oh,
You don't tell me.
No, you.
Ash, Khan, KJ.
K-H.
Wait, I don't know the point. I still hear a question, that's all.
He's pointing at you. When did you?
Up there. Did I forget anyone? Devin. Who else did put up an answer on the board?
Raise your hand.
What's your last name?
RH.
R-A-H. So this time I'll give you guys all a bonus point for a quiz, just for the bravery of actually participating. But in the future, you gotta get it right. If you don't get it right, like no dice.
I'll take it.
What bonus point on the quiz?
On any quiz, just a general bonus point that I'm gonna add to something.
What about your last quiz?
That's two.
Well, whichever quiz. Like I have to look at who gets dropped. One of the quizzes that stick around, I'll attach an extra point to it. It's just, just making it a little fun.
40 is 50 down here.
Let's continue.
I like this incentive, let's do it, let's keep on doing it.
Let's go. Integral test is the next test that we're going to look at. This is test number 3. Telescoping, test for divergence, geometric series. Yeah, so this is number 3. There's something called the integral test, which luckily for us, we're all awesome at integration by now. So there is a way to actually use integration to talk about the convergence of series, and that's because of a very important thing. Suppose we have a series of an and goes from, say, 0 to infinity. And we set, so remember your an you can think of as a function, so that's kind of the idea we're using here. An, we're going to think of it as some function of n, right, where you're plugging in blah, blah. So set an equals to some f of n, right, so I'm going to think of this as a real valued function now, so it's not only working on the integers. And consider this guy. The integral from 0 to infinity of f to the n dn. Now, how do you think that this guy compares to the original? Throw out a guess. What do you think is going to happen? How do these two compare? The integral versus the summation.
One is the sum, the other's like the subtraction of the first term and the last term.
Yeah?
Well, so the integral is basically the area under the curve, right?
Yeah.
And then for summation, you're adding up all values within 0 to infinity. So wouldn't it be equal?
It's not equal. They're not equal in general. No. Yeah, you pulled a U there. You were getting warm, and then you just totally turned.
Am I being mean?
Yeah, that's like that's going to be an adjective now. You pulled a U.
Damn.
Yeah. Yeah, you went like he was, the last problem he was like, it was getting warmer, I'm like, yes, he's gonna get it, and then he's like, combine them now. Like, oh, no, he didn't. Okay, yeah. But yeah, this guy's interpreted as an area, right?
Yeah.
So if my function was whatever, blah, 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 right? And from, say, 0 to infinity, this guy's like an area under this curve, whatever that formula is going to look like, I don't know. How could you graphically think of this guy?
Like y? Actually, not.
You did this last time, like, how can you visualize, well, how can you visualize the sequence? A bunch of isolated dots, right? So if I were to go and plug in 0, it's going to give me some dot over here. Go and plug in 1, it's going to give me some dot over here. Go and plug in 2, it's going to give me some dot over here. Okay, so that's going to be the sequence, right? So what would the summation be? How do you think you can visualize that? Yeah.
The summation would be all of the values of y times x.
Okay. So on this picture, what would it look like?
I don't know, but all I'm thinking of is, I know that is if the integral is the area, then I'm thinking of it what's under, but if it's summation, then it's a bunch of stuff being added together. But with, I feel like I got some, I pulled a U. I don't know if I pulled a U, I think I just straight up went in reverse and left the room.
It's okay.
What do you think a nice picture would look like for the summation? Yeah.
It would just be a trend line.
For a trend line?
Like,
No.
instead of like,
No. I mean, the function itself would be better as a trend line, probably. So here's one way you can think about it. Just think of just like a bunch of rectangles here,
Oh.
right? You're going to create a rectangle in such a way that the area of this rectangle is 1, right? So, so when you take the length times the height, it actually gives you the actual outcome of the thing. So the width is 1. Same thing here. Just think of this as you put up a rectangle whose area represents the actual value that it hits. Right? So remember, the series only works on the integers. So it's like it's adding up values on these strips over here. Whereas the integral is continuous. It adds up all values. So it also takes on values at a half and at a quarter and at pi and all that stuff. So the integral is like all the area under here. Whereas the series is just adding up for the integers, right? It's finding a magnitude for each integer. How do you think these compare? If you were to compare these two, like in general, what would you say? Yeah?
Could you say that AN would be less manageable?
This guy is less than or equal to that guy in general. Right? In other words, if I know this guy converges, then, you know what? This guy would for sure converge as well. Right? Because it's going to be harder for the integral to add up to a value. Because it's actually adding a lot more stuff. Right? So if me adding up all this stuff is going to give me a constant, it's going to give me a number at the end of the day. And of course, this is an improper integral, which we're all experts at improper integrals now. It turns out, if I replace a series with an improper integral, the answer I would get would in general, at least if it's positive, would in general be bigger, right? And so if I can get this guy to converge, then for sure it's going to be a lot easier to get that guy to converge, because this guy has gaps where the other guy doesn't, right? So hopefully this intuition leads to something that we call the integral test. Well, leads to the integral test. Here's what it says. Given a series where an is non-negative, so it's always above, because I don't want the improper integral to be able to dip to negative and then it actually ends up canceling each other out. An is continuous when thought of as a function. Real value function. And 3, an is decreasing. Now, there are a couple ways you can think of decreasing. I don't remember if I mentioned it last time, so I'll mention it now. You could either think of it as the derivative is less than 0, or you can think of it as an plus 1 is always going to be less than or equal to an for all n. So you have a series where these 3 things are true, and you happen to know, you know what? I could actually find an integral of that thing that I'm looking at. So you have this series, you notice these 3 things. If we set f of x to be a model for a sub x, then the integral and the series will both actually do the same thing. Will either both converge or both diverge. Okay. Now, one direction is pretty clear. If this guy converges, then that guy definitely converges, because this guy's going to, in general, give you a smaller answer than that guy. The fact that it goes in the opposite direction, that this one diverges implies that one diverges, that's a little bit harder to see, not too intuitive actually. But it'll do the same thing. If you have a series that fulfills all these conditions, and we need the continuity so that our Riemann integral actually works out, right? Because to apply the fundamental theorem of calculus. Okay. So the idea is, this thing is always positive, so I don't have to worry about this guy canceling parts out, so he actually is smaller than I thought he is. So it's non-negative, it's continuous when I consider it as a function, so I don't have to worry about the fundamental theorem of calculus messing up, aside from the infinity thing. And an is decreasing, because really an is not decreasing, then the test for divergence is going to tell you that it's not going to work. So once you have these 3 things in play, then if you kind of think of the a sub n as a function and integrate it, if the integral works out, the series is going to work out. And if the integral does not work out, the series is not going to work out. So this is called the integral test. It is useful when an is, it's called easily integrable. Okay. It's called the integral test, provided the 3 bullet points. So if you can integrate it, but one of those 3 bullet points don't work out, then all bets are off. So there are going to be times where you're going to see a series. It's not going to be geometric, it's not going to be telescoping, none of that's going to be true. But you're going to notice these three things are true. It's always going to output positive numbers. If I look at it, it's a continuous function, it's never going to divide by 0 or anything like that, and it's decreasing. Then I notice that, hey, you know what, I could actually integrate that formula pretty easily. Then if you actually do the integral in place of the series is going to behave the same way that the improper integral will behave. This is called the integral test. Let's do an example. Silly example, we'll just do one here because I think it's it's easier to visualize than a geometric series. Your geometric series can look all kinds of ways, but yeah, that's a nice one. Okay, so you see a series like that. One thing you'll notice, it is not geometric, it's not telescoping. So you see something like that, here's how you're going to approach it. You're going to notice, you know what, first of all, probably the first thing you actually think if that guy pops up is test for divergence. Does that actually approach 0, right? Now, if you let n go to infinity, what happens to e to the 1 over n? It approaches 0, right? Because you're taking the nth root of e. And you just keep taking a larger root. So the top is getting smaller, the bottom is going to infinity. This is actually approaching 0 over infinity. So it's definitely approaching 0, so the test for divergence doesn't work. Okay, so now you realize test for divergence doesn't actually work. But you do notice that if we set f of x equals e to the 1 over x squared, then your f is continuous on the interval. Your f is also positive on the interval. And your f is decreasing on the interval. Now you can know that the f is decreasing by, well, if I take my f of x to be e to the 1 over x times x squared to the minus 2. Let's write it the other way. X to the minus 2 e to the 1 over x. What is f prime here? Quickly. Negative 2 x to the minus 3 e to the 1 over x. X to the minus 2, derivative of that.
Negative 1 over x squared.
Minus 1 over x squared, e to the 1 over x. So this would look like, well, minus 2 over x cubed, e to the 1 over x, minus 1 over x to the 4th, e to the 1 over x. What can you tell me about that? It's always negative. That's right. Right? The exponential is always going to be positive, and this guy, my x is going from 1 to infinity, so x cubed is positive, and I take a negative of it, so that's now negative. X to the 4th is always positive, taking the negative of it, that's all negative. So the derivative is always negative, so it's decreasing. And we can actually integrate that easy. You should actually know how to integrate that easily. So now, if you consider this integral, from 1 to infinity of e to the 1 over x squared. How do you do that integral?
Can you set u equal to 1 over x?
Okay, there's something you have to do first though. Take the limit. to do that. So now you're just going to integrate this part. Now, of course, you're going to take u equals 1 over x. Your du is going to be that minus 1 over x squared, which is going to give you that 1 over x squared. So this guy actually integrates to minus e to the 1 over x. So I plug in n, that's minus e to the 1 over n plus e. And what's that limit? Yeah?
Negative 1 plus e.
So that goes to well, e minus 1.
Yeah.
And so now, that's it. So that's actually a number. So this means it converges. The improper integral. The integral. But that means the series e to the 1 over n squared converges by the integral test. So there are times when you have a series. I can't tell you a general form for it like I could the geometric series. It's going to look like whatever. It's just going to, you have a series of something where you notice these three things. It's continuous on this interval. It's always going to give me positive outputs. And it's actually a decreasing function. And you know what? It's actually not a bad thing to integrate, right? If you notice all of these things are true, what you can actually do is you can actually use an improper integral to judge what's going to happen to the series. If the improper integral converges, the series is going to converge. If the improper integral diverges, the series is going to diverge. And because it's always outputting positive numbers, you know that if you were, of course, to put absolute values around it, it's not going to make a difference. So whenever this guy actually shows convergence, it shows absolute convergence. So you could even say it converges absolutely. I think we will wrap up there. So we'll pick up with some tests next time. P-series comparison tests, alternating series tests, all that good stuff. Yeah, go. I don't think I said homework yet, maybe I did. But yeah, go over geometric series. You guys obviously have a little bit of issues there. The others, look over this stuff. So the quiz next week will be covering all sequences and series up to the intervals. Cool.